According to UC Davis, environmental toxicology is the study of the effects of chemicals on human health and the environment. There are thousands of chemicals, both man-made and natural, that can negatively impact humans and the environment. By better understanding toxic substances, we can work to ensure exposure is limited and healthy habitats are maintained for all life. Why is copper important within the study of toxicology? Copper is an essential trace nutrient to all life, but it can reach toxic levels. According to the CDC, in the year 2000, an estimated 1.4 billion pounds of copper was released by various industries into the environment. Copper toxicity poses problems for people in that short-term exposure can cause gastrointestinal problems, and long-term exposure can cause liver or kidney damage. While copper toxicity is generally not a major concern for mammals, including humans unless they have Wilson's disease, it can be very toxic to aquatic organisms. To explore copper as a contaminant in the environment, I will describe the chemical nature of copper, its abundance, uses, environmental guidelines, pathways of environmental impact, and review 2 recent studies. The copper atom has a full 3D subshell and only 1 electron in its 4s subshell. Copper is a metal with the atomic number 29 and atomic weight of 63.546. As a metal, it maintains similar properties and environmental behaviors with metal and metalloids, being malleable, forming positively charged ions, the ability to form basic oxides, and being a good conductor of heat and electricity. The natural forms of copper found in the environment are in ores, and trace amounts of its metallic form. Copper has 2 valence states, cuprous, with a valence of 1 is found in cuprous oxide, and cupric, with a valence of 2 is found in cupric oxide. Copper has been used for thousands of years. The Bronze Age began when copper was combined with tin to form bronze in about 3000 BC. Since copper is malleable and a good conductor of heat and electricity, it is currently used in construction, power generation, electronics, plumbing, heating and cooling, telecommunications, vehicles, and coinage. Copper is used in making fungicides, molluscicides, algicides, and pesticides. Copper sulfate is used widely around the world as a pesticide. The world copper reserves are currently estimated at 794 million metric tons. The 3 countries with the largest reserves are Chile, Australia, and Peru. World mining production of copper has been about 20 million metric tons per year, with Chile, Peru, and China leading the way. Also, to look at recycling, copper made from scrap has covered about 35% of the U.S. copper supply. This table lists the environmental guidelines for copper. As you can see, there's about 1,000 times difference between the toxicity level for human health and drinking water compared to the aquatic life criteria. Freshwater toxicity for aquatic life is calculated using the biotic ligand model because there are many variables in freshwater that can greatly affect the toxicity of copper, such as water hardness and the amount of dissolved organic carbon. Also notice a greater than 10 times difference between the residential and industrial soil toxicity guidelines. Even lower than the residential toxicity level is a sediment toxicity level. Inhalation of contaminated dust and certain occupations can present an exposure pathway for copper in humans. In general, most people are exposed to copper through the food they eat and the liquids they drink. The source of copper that is most likely to be a concern for humans is drinking water, particularly water that has been sitting in copper pipes or brass faucets. Since humans are able to handle higher concentrations of copper without negative effects, toxicity is generally of little concern to humans. Lack of copper toxicity in humans and other mammals is for 2 reasons. Copper easily binds to organic matter, reducing its toxicity, and mammals have mechanisms that allows for copper detoxification. The biggest concern for copper toxicity is aquatic environments, with fish and crustaceans being particularly sensitive. There are various sources of copper that result in its toxic accumulation in the environment. The non-point sources of copper in aquatic environments include metal dust from vehicles, treated wood products, pesticides, and anti-fouling paint. Copper can enter aquatic environments from runoff and soil leaching. It can also be deposited from air into water and soil. Although copper does not biomagnify, it can accumulate in sediments in undisturbed soils, which allows the opportunity for copper exposure in plants, microorganisms, and benthic organisms. Some studies show the free copper ion tends to be the form that causes the most copper toxicity in freshwater environments. Therefore, a key point to remember with copper is how its affinity for organic matter reduces its toxicity. Actually, the EPA recognizes that in addition to dissolved organic matter, there are many factors that affect the toxicity of copper in water, including water hardness, pH, and alkalinity. This is why the biotic ligand model is used to determine the toxicity of copper in fresh water. Physiology is another important factor in determining toxicity. Metal has been shown to affect the ability of aquatic organisms to reach their internal ion pools, which can lead to death. According to Paquin et al., quote, research has been shown that the gill is the primary site of toxic action for most metals, unquote. Therefore, understanding the physiology of the gill is very important in our understanding of metal toxicity in aquatic organisms. Keller et al. Conducted a study looking at the possible risks of copper nanoparticles in the environment. They defined risk as, quote, a function of likelihood of exposure at a concentration or dose that may cause harm, and the type and level of harm that may result from exposure, unquote. To examine exposure, they considered the most likely forms of copper nanoparticles to be released into the environment: pesticides and anti-fouling paint. They used high-throughput screening to measure toxicity with cells, embryos, and various organisms. As shown in the slide, the researchers found that the free copper ion was the most toxic, with various forms of copper nanoparticles being subsequently of less toxicity than the free copper ion, but of greater toxicity than the micron-sized copper compounds. In a well-controlled study, Summers, Mudrock, Labinia, and Baldwin show the complexity of toxicology by analyzing the effects of salinity on juvenile salmon when exposed to copper. They say that it has been shown how dissolved copper causes chronic toxicity by negatively affecting scent, behavior, and survival in freshwater, and less so in seawater. But there is little knowledge of how different salinities found in estuaries can affect fish. They believe that this is important because juvenile salmon depend on estuaries for food and survival as they shift from freshwater to saltwater. They created an experimental chamber, and images were captured to see behavioral responses from the fish as copper was released into the chamber at an allotted time. They found that there was an inhibition of the olfactory function of the juvenile salmon in freshwater, but not seawater. In seawater, even at levels of 50 micrograms per liter of copper, there was no negative effect to olfactory function. Avoidance was another factor that was reviewed by them. They reiterate previous studies, which found the lowest observed effect concentration of dissolved copper in fresh water was 0.1 micrograms per liter for rainbow trout and 2 to 7 micrograms per liter for salmon. The researchers have yet to understand how fish sense copper, but they speculate that it may be an irritant to fish because they avoid copper when exposed to it. Concluding their study, they emphasize that dissolved copper causes behavioral changes in juvenile salmon in both freshwater and seawater at levels below what has been measured during a heavy rain. This can negatively affect the ability of salmon to survive during a challenging part of their development. As the human population around estuaries like the Puget Sound continues to increase, this will likely cause copper to be an ongoing problem for salmon, effectively cutting them off from habitat they would ordinarily use.